Hello students, in this video we'll prove the Gauss-Bonnet theorem for simple closed curves. Let's let u of t, v of t be a simple closed curve, just like in Calc 3. On AB. So that just means if I look at this curve and plug in the initial point and plug in the terminal point, the initial point and terminal point have to be the same. There's our curve. We can call this curve over here gamma, for example. I'll just leave it like that for the time being. It looks like this. There's no jumps. So in other words, both these functions are infinitely differentiable. So we can assume that u and v are infinitely differentiable. And so in other words, there's no cusps over here. I don't have a situation where there's going to be a point where the derivative doesn't exist. Just a nice simple curve, right? And let R be a surface parameterization. Like that. Beautiful. Then gamma t, which is R of u of t, v of t, is a closed curve on the surface. Okay, so here's your surface, right? Like that. And then the image under this parameterization of this curve gives you some curve like that, right? So this is your curve gamma over here. Okay? And now what does the Gauss-Bonnet theorem say? The Gauss-Bonnet theorem says in this case that if I integrate over the curve gamma, the geodesic curvature, that is 2 pi minus the double integral over the interior of gamma of the Gaussian curvature with respect to the surface area differential. Okay, beautiful. That's a wonderful theorem that relates the global curvature, right, on the interior of the curve to the geodesic curvature on the boundary. Okay, and so here's what we're going to do. We're going to let Fg be an orthonormal basis of the tangent space to the surface at every point, okay? As I said before. So I choose an orthonormal basis. I can do this by Gram-Schmidt. We already know properties of this orthonormal basis, right? Then, if theta of s is the angle between f hat and gamma dot, then gamma dot is going to be f. I'm going to suppress the of s here, right? Just cosine of theta plus g hat sine theta, because it's an orthonormal basis, I can write down this expression. And then this implies that the component n cross gamma dot has to be what? Has to be f negative f hat sine theta plus g hat cosine theta. Okay, beautiful. And now, of course, here comes the second derivative has to pop up, because I know if I take this expression over here and dot this with gamma double dot, that gives me the geodesic curvature. So let's do that. So what's gamma double dot going to be? So here's the tricky part. So gamma double dot is going to be f dot cosine theta plus g dot g hat dot sine theta, then minus f cosine theta, theta dot, and then plus g hat cosine theta. Oh, I don't have to do the derivative. So that's going to be a sine, of course, right? Because derivative of cosine is sine. So it's going to be an f hat sine theta theta dot plus g hat cosine theta theta dot. Okay? So what's my kappa g going to be? So let's do it slowly. So my kappa g is going to be what? Kappa g is going to be, well, let's do this over here. So we're going to have a, now what do we know? So here's an elementary observation. So what can I say about, I know that f hat dot g hat is equal to 0 because it's an orthonormal basis. And I also know f, any derivative of f hat dot f hat is equal to 0, and g hat dot g hat is also equal to 0 because they're unit vectors, right? Good. All right, so those are things that we're going to use in our calculation over here. So if I do, for example, if I do this term over here dot this term, it's 0 because f hat dot f hat dot is 0. So these first terms are going to be a what? An f hat dot g hat cosine squared theta. So the dot over there goes on the f. Then what do we do next? Then I got to do this term. So this dot, the g will be 0 because of unit vector. So I'm going to get a minus f hat g hat dot sine squared theta. Good. And then that takes care of these terms over here, right? Then if I have f and then f, that gives me a 1 by a unit vector. So that's going to be just a sine squared theta dot plus sine squared theta dot. And then f dot g is equal to 0 by orthogonality. G dot f is equal to 0, and then g dot g is equal to 1. So this is going to be a plus cosine squared theta dot, right? I'm going to do one thing over here. I'm going to take this derivative over here on the f dot and pass it to the g dot. So all total, the geodesic curvature is going to give me what? The geodesic curvature, these terms just add up to theta dot. So I get a theta dot over here. And then we have minus f hat g hat dot, right? And then if I do that, or if I put the dot over here, that's a negative cosine squared theta. Negative sine squared theta, that gives me just a negative 1 over here. Beautiful, right? And so now what do we know? I'm going to write down what g hat is going to be, right? On this curve, this is going to be theta dot minus f hat. And then we're going to have a g hat u dot plus g hat v dot, like that. Okay, so that's a little bit of a nicer expression. Now let me integrate this. Okay, so if I integrate kg, that's the same as integrating this over here. So the integral over gamma of the geodesic curvature, ds, is going to be, well, if I integrate theta dot, that's a perfect derivative. Integrating theta dot around the closed curve gives me 2 pi. Okay, now that's actually, I'm sweeping something important under the rug over here. What I'm sweeping over here is the fact that theta integrates over the unit circle to that the integral over gamma theta dot ds is equal to 2 pi. This is an important relationship. It's true for any simple closed curve, and that's known as the Haupt-Umlaufsatz. And we won't prove that in this video because it requires homotopy theory, so we need a little bit of homotopy theory in order to prove this theorem. But you can think about what happens in the case of like a circle, for example. If you measure how much the angle is changing as you traverse the unit circle, it changes by 2 pi, right? That's how much the circle changes. Now, of course, you can sort of think if I deform the circle a little bit, so there's the case of the circle is easy, but if I just deform the circle to some other sort of strange curve like this, well, in that case, it's basically still encapsulated. I can basically take that more strange curve and continuously deform it onto the unit circle. So if there's that's what a homotopy is, right? So in other words, if two curves are homotopic, then I know they're going to share the same index or the same winding number, right? So that requires a little more work, but intuitively it should be obvious that gives us 2 pi, okay? Good. And then minus this thing over here. F hat, and then G U du. That's a U. And then a plus F hat G V dV, like so, ds. Okay. Get rid of the ds. Now that's just a regular line integral, right? I write the ds as a line integral now, okay? And now, of course, I can tee up Green's theorem. And you should have expected Green's theorem because it's the interior of gamma over here, right? So let me use Green's theorem. So it's going to be 2 pi minus the double integral over the interior of gamma. And then I got to do the what? I got to do the u derivative of this. And then minus the v derivative of the first thing, the v derivative of this thing over here. F, G, U. And that's going to be a dA. Okay? Not a d sigma, right? But what do we know about this? When we do this product rule, I'm going to have an FUGV, then I'm going to have an F, then I'm going to have an FGVU, and over here I'll have an FGVU. So when the derivatives go on the GV or when the derivative goes on the GU, those terms are going to cancel, and you'll just have an FUGV minus FVGU. So these terms over here are going to work out to be what? Those will work out to FUGV minus FVGU. And we have from our previous lemma that that's exactly equal to what? That's exactly equal to the ln minus m squared over the square root of EG. So that this whole thing was going to simplify to what? This whole thing just simplifies to 2 pi minus the double integral over the interior of gamma. And then just the Gaussian curvature k d sigma. And what we're really using here is we're using what fact? We're using the fact that this quantity over here is equal to ln minus m squared over the square root of EG minus f squared, right? We have that from a previous video. Now, of course, that's not k, but if I put in an extra factor, EG minus f squared over EG minus f squared, then this expression over here is the what? That expression is the Gaussian curvature, because now it has the right form, and what's left over adjusts the area differential into the surface area differential, and that proves the first version of the Gauss-Bonnet theorem, which says that if I integrate the geodesic curvature over the curve, that's 2 pi minus the Gaussian curvature over the interior of that curve. Beautiful result. In further videos, we'll extend this to the case when you don't have a smooth curve, you have cusps on your curve, and that basically introduces more angles into the problem. Thank you very much.